Okay, so here's a Zoom meeting for Physics 232C. We'll usually have these Zoom meetings Monday. Monday is at 7 p.m. And we'll go over the chapter that we're studying at that time. So we've finished chapter 15, and now we're working on chapter 16. For each chapter, there's a recorded lecture at the YouTube channel. So take a look at those YouTube recordings. That may help you get started on studying the chapter rather than just diving straight into the reading. Get a little introduction to the subject, find out what it's going to be about, learn some of the language, learn some of the words, and then study the chapter. Of course, the YouTube introduction is not a replacement for actually reading the chapter. You'll have to read the chapter and take notes. You should have a physics notebook. As you read the chapter, probably take 2 or 3 hours to read the chapter. As you're reading the chapter, take notes in your notebook, about 1 page of notes, front and back. Mainly equations, so that you'll have the equations easily accessible when it comes to doing the problems. So you won't have to leaf back through the book to find the right equation. Now, chapter 15 was on the electric field, and the electric field is a force field. So it's defined in terms of the force that it exerts on charged particles. The electric field is the force divided by the charge on a test charge. Now, if you think back to Physics 231, which you've taken before, along with force, there's energy. In mechanics, we have forces, we have potential energies. In electromagnetic field theory, we have force fields, the electric field and later the magnetic field, and we have field energies. So the electric field is not just a mathematical quantity that we define to describe the force. It's a real physical thing which has energy. It has energy just as much as a particle has energy. And so the electric potential is related to the energy of a system of charged particles. So you've probably already read chapter 16. A lot of people have already started working on the problem assignment. Anyway, if you've read the chapter and you've taken notes, these are the kind of equations you should have written down in your notebook. You should know these equations and know what they mean, understand them. There's potential energy when you have a system of charged particles. The simplest thing would just be to have 2 charged objects with charges Q1 and Q2 separated by a distance r. Think of these as little spheres, and r is the distance between the centers of the 2 spheres. Well, there's a potential energy. I call it potential energy because it's an energy which is not kinetic energy. It's not kinetic energy related to the motion of the particles. It would probably be better to call it field energy. It's actually electric field energy. But the authors of this textbook call it potential energy. And so the potential energy, we could call it U, for a system of 2 charges is K, Q1, Q2 over R, where K is Coulomb's constant. We saw that back in chapter 15. Remember, the force is K, Q1, Q2 over R squared. The potential energy is K, Q1, Q2 over R. Now that's energy. We also define another quantity, which is called the electric potential. And while we'll use the letter V to stand for electric potential, the electric potential associated with one charge is KQ divided by R. So, we have the electric field of a single charge is given by the equation KQ over R squared times R hat. Electric field is a vector, so you have to give it a direction. R hat is the direction directed away from the charge. Well, electric potential is not a vector. It's a scalar. So it doesn't have a direction. It just depends on the charge and the distance that you are away from the charge. You have a charge at some point. Throughout the entire volume around that charge, so that could be the charge Q, at any point around in this volume, there's a value of electric potential, which is just KQ divided by the distance from the charge. And that's the meaning of electric potential. And now if you read the chapter, you know the relationship between potential energy and electric potential. Potential energy is the potential times a charge. So if I multiply by a charge, you see I'd get K Q1 Q2 over R, which is this equation. Now we use the letter V for potential because that's voltage. The unit of V is the volt. There's a relation between field and potential. The change in potential across some displacement delta x is negative E delta x, negative E dot delta x. This is a dot product of two vectors. Displacement will be a vector. So E dot delta x means the length of E times the length of delta x times the cosine of the angle between the two directions. And you have to add all of those right across from the full displacement. That'll give you the difference in potential. Remember the delta notation. That'll give you the difference potential from one end of the displacement to the other. Or we could say the electric field at some point is negative the change in V over a small change in X. So, if I come here, the electric field points this way. So in other words, the rate of change of the potential, change in the potential divided by the change in position, that's the rate of change in position with respect to space, is the negative of the electric field. The electric field points in the direction from high electric potential to low electric potential. Now that gives us, again, a unit. The unit of the electric field, because of this relationship, is the numerator here, that's volts, divided by the denominator, that's meters. So the unit of electric field could be written as volts divided by meters, because it's the rate of change of the potential per unit of length, in space. Back in chapter 15, we used a different unit for the electric field. Back in chapter 15, we used that the electric field has the unit of newtons per coulomb, because the electric field was equal to the force divided by the charge. The numerator force is newtons, charge in the denominator is coulombs. So volts per meter is the same as newtons per coulomb. Volts per meter and newtons per coulomb are the same thing. And that's one way to define the volt. A volt is a Newton meter per coulomb. Now, if you think back to mechanics, Newton meter is a joule. So a volt is a unit of energy divided by charge, as we can see from these equations. So volt per meter is the same as newtons per coulomb. And, you know, when you're doing a log kappa problem, you could give the answers in terms of volts per meter, or you could give the answers in terms of newtons per coulomb. Those are the same thing. Now, as an example of voltage, a good portion of chapter 16 is about capacitors. If you've read the chapter, you know a capacitor is just a pair of two conductors, two pieces of metal. Two pieces of metal make a capacitor. And the two pieces of metal will have equal but opposite charge if the total charge is 0. So we could have two pieces of metal with equal but opposite charge. So one positive, one negative. The electric field would point from the positive plate to the negative plate. So that's the electric field, and that's throughout the volume between the two plates. The electric field is primarily concentrated in the region of the volume between the plates. And we know from, what creates an electric field? Well, charge, that's one thing. So the electric field will be proportional to the amount of charge. We have here total charge 0, but it's divided into two parts. There's Q on the upper plate and negative Q on the lower plate, or on the negative plate. So the strength of the electric field will depend on that Q. It'll be a linear function of Q. And the electric field is proportional to potential. So that means the ratio of Q divided by the potential is a constant that doesn't depend on Q. Delta V is proportional to Q. Delta V is equal to Q divided by C. So C is Q over delta V. C is just a constant, doesn't depend on the charge. It will depend on the size and shape of the capacitor. All right, so this is what you should get out of reading chapter 16. These equations should be in your notebook. You should understand what they mean. And now let's go over some problems to see how these equations describe electric systems. So here's a problem which is in the homework assignment. So problem set 2 is due on Wednesday, and this is Monday. A lot of people have already done some of these problems, but anyway, let's take a look at several problems. Here's one about the hydrogen atom. The hydrogen atom is the simplest of all atoms. It has one proton in the nucleus, one electron moving around outside the nucleus. The total charge is 0 because the proton has charge plus E, The electron has charge minus E. So the total charge is 0. But there are charges, equal to opposite charges, and they exert forces on each other. They're held together, and that forms an atom. That's the simplest possible atom, a hydrogen atom. And probably a lot of you have taken a course in chemistry. So you know how the hydrogen atom is the simplest atom. More complicated atoms will have a larger charge in the nucleus and an equal number of electrons to give total charge 0. Now, the first theory of the hydrogen atom was by Niels Bohr. The Bohr radius is the most probable distance between the proton and electron in the hydrogen atom in Bohr's theory of the structure of the atom. So we're not going to use the Bohr model here. We're just going to use the value of this constant. Of course, there can be excited states of the atom, in which case the distance is larger. But for the ground state, the lowest energy state, the most probable distance is the Bohr radius, which is equal to 1 A0, which is 0.529 angstroms. An angstrom is 10 to the minus 10 to the minus 10 meters. Oh, here it is. 1 angstrom is 10 to the minus 10 meters. So a unit of length that's often used in atomic physics is the angstrom. In terms of ordinary standard units, it's just 10 to the minus 10 meters. It's very small. In terms of the engineering unit, like a laboratory unit, like a meter, it's 0.000000000001. It's very small. So the problem in this, the question in this problem is, what's the electric potential produced by the proton at a distance of 1.19 Bohr radii? And then the second part is, what's the potential energy of the system when they're at this distance apart? So we do all problems in the same way. We have this general method. We draw pictures, label the pictures. We write the relevant equations. Then we analyze the equations using algebra to get an expression for the quantity we're trying to calculate. And then we use a calculator to compute the answer. So what would be the relevant equation? Well, here's the picture. It's a proton and the electron moving around. In the old Bohr model, it was assumed the electron is just on a circular orbit, but that's not true. In the more modern quantum theory, the electron sort of spread out in a spherical shape. It's like a cloud of negative charge. All right, so what are the relevant equations? Well, we're talking about the electric potential. That's what we're trying to calculate. So let's write down the equation for the potential. Potential is K times the charge over R. Now, which charge is this? This is the potential produced by the proton. So that is the proton charge. And K times the charge divided by the distance is the potential, the voltage produced by that proton. Now, what about the potential energy? Because that's part 2. Well, potential energy is K times Q1 times Q2 over R. Remember, that was on my page of equations. So you've got that written down in your notebook. Well, Q1 is E, and Q2 is negative E. So the potential energy is negative K E squared over R. And those are the only equations we need. Now, the rest of it is just calculating the numbers. Well, the numbers and the units. So we're going to take R to be 1.19 Bohr radii, and that's approximately 0.6 times 10 to the minus 10 meters. This is only approximate, but we'll get a reasonable number. The potential is K, remember from chapter 15, K is 9 times 10 to the 9th. Newton meter squared per coulomb squared, or Newton meter squared is the same as joules times meter over coulomb squared, times E, 1.6 times 10 to the minus 19 coulombs, proton charge, divided by R, 0.6 times 10 to the minus 10 meters. And now that's going to be the answer to part A. It's a number with a unit. So we'll calculate the number using a calculator, but let's first figure out the unit. I have here joule meters divided by coulomb squared times coulombs. So that'll be joule meters divided by coulombs. 1 power of coulomb will cancel. And now I have meters in the denominator. So this will be joules divided by coulombs. And now if you remember the definition of a volt, that'll be 1 volt. So the unit, as we see, is joules divided by coulombs. A joule divided by a coulomb is a volt. And now what about the number? Well, you could do it with a calculator, but you could try to figure it out just estimating. Here's 10 to the 9, here's 10 to the minus 19, so that's 10 to the minus 10, divided by 10 to the minus 10. So the powers of 10 cancel out. I just have 9 times 1.6 divided by 0.6. So this is, I don't know, this is 9. Well, anyway, it's about 24. So approximately it's 24 volts. Now, what about the energy? Well, the energy is minus K E squared over R. So that's minus 24 volts times the electric charge, E. And electron volts is a unit of energy, often used in atomic and molecular physics. So in fact, I could just express this in electron volts. So if I express the energy in the electron volt unit of energy, it's negative 24 electron volts. And that's a characteristic energy of an atom, say a hydrogen atom. It's not all the energy because it doesn't take into account the kinetic energy, but it's the potential energy of the charges in an atom. All right, so that was a problem from problem set 2. Just making use of the idea of potential energy and voltage. But now let's go on to another problem, which involves capacitance. So this is going to use some of the equations which you should have written down in your notebook concerning capacitors. This concerns the simplest kind of capacitor, a parallel plate capacitor. A capacitor is just a pair of conductors. But the most familiar kind of capacitor is 2 plates, 2 parallel plates, 2 parallel pieces of metal, or little metal foils. 2 foils separated by a non-conducting medium, could just be air, is a parallel plate capacitor. And here's the electrical engineer's symbol for a capacitor. It's 2 plates. The geometrical factors are the area of each plate, just take them to be equal areas, and the distance between the two plates. So we'll call that the separation distance. So here's a kind of typical simplified view of a capacitor. And this is the electrical engineer's symbol of it for a circuit. All right, so what's the capacitance? So that's part A. What's the amount of charge and energy stored when it's attached to a battery with an electromotive force, E? The electromotive force, every battery has two electrodes, a positive electrode and a negative electrode. And as long as the battery is not, run down, it'll have a characteristic voltage difference, or it'll have a constant voltage difference between the two electrodes. So this is the electrical engineer symbol for a battery. It's got a positive side and a negative side. And the potential difference between the positive side and the negative side is called the electromotive force. It's called E. It's a voltage. E is another voltage. All right, so there's the picture with a capacitor. Oh, by the way, this positive voltage is on one plate of the capacitor, so that plate will pick up a positive charge from the positive side of the battery. And the other side of the capacitor will pick up a negative charge from the negative terminal on the battery. And these will be equal and opposite. So we'll have a charged capacitor with charge separation Q. Of course, the total charge is zero, because it's plus Q on one side, minus Q on the other side. But it's separated charge. And so the separated charge is Q. I could say the separated charge is actually 2Q, but we call this a capacitor charged to Q. All right, so we're given the area, we're given the separation, we're given the EMF. Now here's one of the equations you should have in your physics notebook. Capacitance of a parallel plate capacitor. It's a universal constant, epsilon zero, times the area divided by the separation. The bigger the area is, the larger the capacitance is. The smaller the separation is, the bigger the capacitor is, or the bigger the capacitance is. And so that's a formula which you'll find in chapter 16. Epsilon naught is related to the Coulomb constant. Epsilon naught is 8.85 times 10 minus 12. It's farads per meter. Farad is the unit of capacitance. The area is given here as 2.59 times 10 minus 3 square meters. Separation is 0.052 millimeters. So that's 5.2 times 10 to the minus 5 meters, converting it to standard units. You always want to convert all the lengths to meters. So we'll convert these 0.05 millimeters to 5 times 10 to the minus 5 meters. So that's the answer to the first part, the capacitance. It's a number with a unit. So we'll calculate the number with a calculator, but let's just look at the unit. It's farads per meter times meters squared. So in the numerator, I have farads times meters. And then in the denominator, I have meters. So the meters cancel, I just have the unit farad. That's the farad unit named for the great Michael Faraday, who did many of the earliest studies of capacitors back in the early 19th century. And as for the number, well, here's like 10 to the minus 11. Here's like 2 over 5. So 2 over 5 would be like 1 over 2, 8 over 2 would be 4, so it's more like 4. The powers of 10, 10 to the minus 15 over 10 to the minus 5 would be 10 to the minus 10. So there's the number. But you'll want to calculate the number accurately using your calculator. Now all right, so that was part A. Part B was to find the charge and energy. Well, charge is easy because the definition of capacitance is charge divided by voltage. So charge is then capacitance times voltage. We already calculated capacitance. The voltage is given. No, the voltage is 49 volts. So that's easy. What about the energy? Well, again, that's something you'll find in the chapter 15. You should have written it down in your notebook. It's 1/2 times the charge times the potential difference. Or I could write that as 1/2 charge is CV. So I could put in there C times delta V times another delta V. So 1/2 CV squared. 1/2 capacitance times voltage squared. That's energy. That's the energy. That energy belongs to the electric field between the plates. That's electric field energy. What's delta V? Well, delta V is the voltage difference between the plates. Since they're attached to the battery, the voltage difference between the plates is just the voltage difference between the terminals of the battery. So if this is a 3-volt battery, that means the positive plate has, let's say, potential 1.5. The negative plate has potential minus 1.5. The difference in the potentials is 3 volts. That'll also be the difference in potentials of the plates on a capacitor. Because when a conductor is attached to a battery, the voltage of the conductor is the same as the voltage of the terminal on the battery. But it's attached in 2 places. So anyway, you would plug in the numbers here. No. I want to go back here, don't I? So 1/2 CE squared. C I calculated up here. 4 times 10 to the minus 10. E, well, it depends on what E is, but here it says it's 49 volts. E squared will be a large number. That'll give you farad volts squared. And a farad times a volt is a coulomb. Farad times volt is coulombs. So this will have units coulombs times volts. And a coulomb times a volt is a joule. That's the definition of the volt. A volt is 1 joule of energy divided by 1 coulomb of charge. So I'll get an answer in joules. Okay, any questions about these 2 problems? You can either write a question on the chat little panel, or you can just speak up. All right, so now we got one more problem we can consider. So here's one more problem. It refers back to the preceding problem, namely this picture. Find the energy per unit volume between the plates. That's electric field energy. So this is going to give us an idea of how much energy does an electric field have. So we're going to calculate the energy per unit volume. Well, the energy we already calculated. It's 1/2 C times E squared. Now, what's the volume? Well, the volume between the plates is just the area times the separation. So the energy density, energy per unit volume, is the total energy. That's the 1/2 C E squared that I did in the previous problem, divided by the volume. Area times the separation is the volume between the two plates. So, we have the area, we have the separation. We calculated U. I guess the numbers have changed a little bit, but we know how to calculate U. It's just exactly the same as the previous problem. So you can calculate U over A times S. U will be joules. It's an energy. A times S will be meters cubed. So energy density will be joules per meter cubed. Just like mass density is kilograms per meter cubed, energy density is the amount of energy per volume. So that's joules per meter cubed. Then in part B, it says, calculate epsilon naught E squared over 2. Just for comparison. So, here's a picture of the plates and the electric field between the plates. Well, remember the relation between electric field and potential difference. The electric field is the potential, the change in potential over the same change in position. And the change in position is the separation between the two plates. So the electric field is just the electromotive force divided by S. And now if you do this calculation, so you know what potential difference is, it's 44 volts. So you put in here the 44 volts, you know what the separation is, it's 0.05 millimeters. Well, then you find out what's the electric field. That'll tell you the electric field between the plates. And now calculate epsilon naught over 2 E squared. And just compare it to the answer you just got. Epsilon naught is that universal constant. I guess you should have that written down in your notebook because you're going to need it over and over again. You might as well have a place where it's easy to get to. And so now you just pick up your calculator and calculate this epsilon naught over 2 E squared. And lo and behold, these are equal. In fact, that's a general result. The energy density of an electric field at some point is 1/2 epsilon 0 E squared at that point. So this is the amount of energy in a small volume around X divided by that volume. So that gives you the energy density. And it's just proportional to the square of the electric field strength at that point. So this tells you how much energy is carried by an electric field. It's proportional to the electric field strength squared. And we'll find a similar formula for magnetic fields, and we'll apply those formulas when we come to the theory of light, because light is an electromagnetic wave. So the energy density in light, which is by definition the density, the intensity of light, how bright is a beam of light, what's its intensity? Well, it goes like the electric field strength or the magnetic field strength, or actually the combination of the two. So, I put in U 1/2 C EMF squared, put in volume AS. Remember, C was epsilon naught A over S. So here's the C, epsilon naught A over S. E, the electric field, is E, the EMF, divided by S. So I have here E squared S squared is the electromagnetic field squared, the EMF squared, divided by AS. See, the A's cancel, the S's cancel. It's just 1/2 epsilon naught E squared. So it's not a coincidence. It's just a fact of electricity and magnetism, that the electric field carries an energy whose density is 1/2 epsilon naught E squared. So that's a very general result, which we can use in many ways, but in particular, we can use when we come to the theory of light. All right, so we've already used about 45 minutes. Any questions? I guess you've already finished the problem set number 1, which is for chapter 15. So that's already finished. You have the reading quiz for chapter 16 due the end of tonight. A lot of people have already finished it. And then you have these problems, or the problems associated with chapter 16, are due Wednesday. Then we go on to the next chapter. Okay, anybody want to ask a question? You can either put it on the chat or you can just speak up. Unmute your microphone. Well, we'll have another Zoom meeting a week from today. Oh, here's a question. Can we go over the last question of the reading quiz? I don't remember what the last question of the reading quiz is, but let's see if I can find it. If I go to Lon Kappa, let me find the reading quiz. So this would be reading quiz 2. It's due the end of tonight. I might as well stop the recording.